So 13.3. Counting. Permutations and combinations. All right, let's start out with thinking about choosing how the clothes that we're going to wear to come to school. So let's say, started with an example. Let's say I have 4 shirts that are clean and 2 pairs of pants. And I want to figure out how many different outfits I can put together to wear to school. So how would I figure that out? Multiply 4 times 2. Okay?
Okay, yeah.
Where you're gonna?
Well, I was thinking you have to multiply 4 times 4 and 2 times 2 and add it.
No, yeah. I think you're thinking of something else.
Yeah.
Maybe what we're getting to. So to figure out how many outfits we have, we multiply 4 by 2. But for each pair of pants, or for each shirt, I can wear 2 pairs of pants. So I can make 4 times 2, or 8 outfits. And one way we can think of this, and this works for smaller numbers if you're not sure, I can make what we call a tree diagram. So for shirt 1, I could wear a pair of pants 1 or 2. For shirt 2, I could wear a pair of pants 1 or 2, and etc. For shirt 3, 1 or 2, or for shirt 4, 1 or 2. And if I count all these up, I get 1, 2, 3, 4, 5, 6, 7, 8. 8 combinations of pants and shirts. So when we set things up like this is called a tree diagram. And if we had more shirts, if we had more pairs of pants, we would just add more branches to the tree. If we had 2 pairs of socks that we could go with each one, for each branch out here, I would put a pair of socks. So if I'm just going to add on to my problem here. If we have, instead of socks, I'll say 2 belts. 2 belts. So I'm adding on to the original problem. So shirt 1, pair of pants 1 or 2, I can add a belt on also. Whoops. And this gets complicated really fast because I'm adding all these things on. You can see the numbers get big really fast when we combine things like this. So my tree diagram gets big really fast. So the red is belts. So now I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Well, what's another way I can get 16?
4 times 2 and then add another 2, so 4 times 2 times 2.
4 times 2 times 2. So I have 4 for the shirts times 2 for the pants times 2 for the belts. And if we wanted to add more stuff on, for each additional thing we'd add on, we would multiply again. So this gives me 16, just like we counted over here. So the tree diagram and this way of multiplying are two different ways of counting these ways of putting things together. We call this multiplying the different possibilities of ways of putting things together. We call this the fundamental counting principle. So when you see that vocabulary word, that phrase, you'll understand what it's talking about. So let's write that down. Fundamental counting principle, and the way it's phrased is it sounds kind of complicated, but it's not. So we say one event happens m ways. M is just a number, some number m. And another, remember, an event is just something that we're interested in. Another event happens n ways. Just some number. M and n are just some number. Together, they happen m times n ways. So this multiplying the two numbers together is what we call the fundamental counting principle. So that gives us a way to figure out to count really big numbers. So for example, if instead of 4 pairs of pants, if I had 10 pairs of pants, and I had 20 shirts, and 3 belts, and 15 pairs of socks, and I wanted to figure out how many different ways I could put them all together, making that tree diagram, you'd be drawing tiny little branches and it would go all over the place. But you can just multiply those numbers together, and you know how many possible outfits you have. Probably not all of them would go together because not all your socks and shirts and pants would match. But that would be a way to figure out the number. So questions on fundamental counting principle? All right, let's look at another. Yes. So this is like we're talking about with our shirts. So the first event that we talked about in our example was 4 pairs of pants. We have 4 pairs of pants. So that was our event, having 4 pairs of pants. The other event was having 2 shirts. So we can put the 2 shirts and the 4 pairs of pants together. That's what I mean by they happen. We can put them together and we multiply those numbers together to figure out how many ways we can put them together. Okay. And that's a good question, because I said an event happens, but back here we're talking about having a shirt. So it seems like nothing really happened. So our event is just having the shirt. So it happens that we have that shirt. Okay? All right, so let's look at an example. We want to make a password. From one letter and 2 numbers from 0 to 9. So I'm going to say 2 one-digit numbers. And I'll put in parentheses 0 to 9. How many passwords can we make? So that's our question. How many passwords can we make? So we have one letter and two one-digit numbers. So for the letter, how many choices for the letter do we have? 26. There are 26 numbers in the alphabet. So for the letter, I'm going to write a little 26. We're going to use the fundamental counting principle here because our first event here is one letter. Our second event is a one-digit number, and then we have a third one here. Our third event is a one-digit number. So we want to figure out how many ways those can happen together. So for one letter, we have 26 possibilities. We're using the fundamental counting principle, so I'm going to multiply. How many one-digit numbers can we have for the second part of the password? 9 or 10? 10, we're counting 0, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 isn't a one-digit number. So we have 10 one digits. 0 through 9 is 10 numbers that we can pick. So number one, we have 10. And how many numbers can we pick for the second number? And we're allowed to repeat. 10 again. So I multiply those together, and I get 2,600 possible passwords from one letter and two one-digit numbers. So those numbers get big really fast. Now, what if I change the problem a little bit? What if I said, I wanted to make a three-letter password, but I can't repeat letters? Well, let's look at that one. So a three-letter password with no repeats. So how many choices do I have for the first letter? 26. How many choices do I have for the second letter? 25, because I can't repeat. And how many does that leave for my third letter? 24. And I'd have to multiply that out. Times 24, I get 15600. So 15,600 three-letter passwords if I can't repeat letters. That's a lot of three-letter passwords. So that gives you a hint as to when you're making passwords for logins, why they want 8 digits and they want special characters and they want capitalization, because the more things that they change, the harder it is for people to figure out what those passwords are, because there's a huge number of possibilities. But one thing computers are good at is cranking through and trying one, then the next, then the next, then the next, then the next. So that's why they want to make them as complicated as they can. All right. Questions on fundamental counting principle? What it's telling us is when things happen together, we multiply to figure out how many ways they can happen together. All right, let's look at another example and come up with another way of describing what we're talking about here. Another way. So let's say we want to put 5 books on a shelf. How many arrangements? So we're going to use the fundamental counting principle. So I have my books sitting here on the table, and I'm going to pick them up one at a time and put them over here on my shelf. How many choices do I have for the first book? 5. How many does that leave for the book in the second place? 4. How many does that leave for the third place? 3. And then we have 2 times 1. If I multiply this out, 5 times 4 times 3 times 2 times 1, what do I get? 120. Yes?
Are you sharing that one stack?
Did I keep them all?
You kept them all, okay.
Yes.
That's okay, I just
Okay.
wondered. Okay.
All right.
Thanks.
Sorry. So we have 120 ways that we can put these 5 books on our bookshelf. So this calculation of starting with a number and multiplying by each smaller number until we get down to 1 happens a lot. It happens really often, especially when we're talking about probability, when we're talking about counting big numbers. We have come up with, mathematicians came up with a special symbol for it. So what we do is we say 5 times 4 times 3 times 2 times 1. We write that as 5 factorial is the way we pronounce that. So this is 5 factorial. That exclamation point is, we pronounce that factorial. And it means start at whatever number and multiply by each smaller number until we get to 1. And just to make everything work out right, we say that 0 factorial equals 1. And this is always true. So otherwise, the rules for factorials don't work out the way that they would make sense. So we say that 0 factorial equals 1. So let me show you, I have a calculator here. I want to show you on the calculator. So if your calculator doesn't have this particular button, you can always do it this way, 5 times 4 times 3 times 2 times 1. But most scientific calculators are going to have either a factorial button or a way to get to factorial. So if you have most of the normal TI scientific calculators, the factorial is in this PRB button. Let me make this a little bigger. There we go. This PRB button means it means probability. So if I press that, I get a menu, and I'm going to go down to factorial, and there's my factorial. So let me clear out of there. So I'm going to do 5 probability, and then go down to factorial and hit enter. So it says 5 factorial, I hit enter again, and there's my answer, 120. Some calculators will have that exclamation point, the factorial, on a button. If you're not sure how to get that button, that thing on your calculator when you're using your calculator, I can show you while we're working. Yes?
So if it was like a bigger number, like 10, then would the factorial multiply by all numbers less than 10?
Yes, so that's a good question. Let me write that out. So the question is, 10 factorial would be 10 times 9 times 8 times 7 times 6, a lot of numbers, times 5 times 4 times 3 times 2 times 1. And that's going to be a huge number. Let's calculate 10 factorial on the calculator. 10, that would take a long time to do by hand. 10 factorial. So that is 3,628,800 is 10 factorial. So if I had 10 books that I was putting on a shelf, I would have over 3.5 million ways that I could arrange them on my shelf. That's a lot of arrangements. So again, on your calculator, if you're doing these things, If you're not sure how to get to those buttons, those menus, whatever, I'm really good at figuring out on all kinds of different calculators. So we are going to use factorials to calculate another way of counting things called a permutation. So that's what we're going to talk about next. Permutation is when we are only instead of counting, instead of putting all the things together, we're only taking a portion of a list of things. So we're taking 3 out of 7 things. We're taking 5 out of 11 things. How many ways can we pick 5 out of a group of 11? And there's another special thing that happens with a permutation. So let me tell you what a permutation, how we calculate a permutation, and then we'll do some examples of permutations. So the number permutations, and permutation is just a special kind of arrangement. The number of permutations of n things, so n is just a number, 10 things, whatever, arranged r at a time so 10 things arranged 3 at a time, for example. We're picking 3 things out of 10. I'm picking 5 students out of a class of 36, whatever. And for permutations, we say the order matters. And I'll get to talk more about what I mean by order matters. And we write that in PR. The big P stands for permutations. N is the number of things we're picking from, and R is the number that we're picking. And the way we figure that out is n factorial divided by n minus r factorial. So let me do an example of calculating a permutation, and then we'll explain what we mean by the order matters. So if we just wanted to calculate 7p4. So we're picking 4 things out of 7, is what this is saying. I'm just going to plug into my formula. N here is the number of things that we're picking, so the big number goes on top. And I have to put parentheses here. So n is the big number, r is the smaller number. One thing to be careful of, we can't distribute the factorial. We have to do the parentheses first, so we can't distribute the factorial. Question?
So then, when you simplify that, it would be 7 times 6 times 5 times 4, so on, and then divided by 3 times 2.
Right. So let me write that out. That was a good question. 7 factorial, 7 minus 3, 7 minus 4 is 3. So this would be 7 times 6 times 5 times 4 times 3 times 2 times 1 divided by 3 times 2 times 1. Now, if you can always simplify it to this and do the factorials in your calculator, or if you can't remember how to do the factorials in your calculator, you can always just go and do it the long way like this. It's pretty easy to make mistakes this way, but you can always do it this way. So let's calculate this out. I'll show you two different ways on the calculator. So let me clear this. So I'm going to do 7, and then I'm going to go down to factorial, and I'm going to divide by 3 and go to the factorial. So there's what the calculator says, 7 factorial divided by 3 factorial. And I hit enter. 840. The other way that I can calculate it is some calculators have this button on the calculator. So let's go back to the calculator. I'm going to do 7. I'm going to go to my probability, and it has this NPR button. I'm going to push 7, NPR, 3, and hit enter. You know what I forgot up here? I forgot some parentheses up there. So what I calculated here on the bottom is 7 factorial divided by 3, and then it did the factorial of that whole thing. So let me recalculate that. 7. So it's something to be careful with on your calculator. Divided by, and then I'm going to put some parentheses. 3 factorial. And a parenthesis. Yes.
Your issue was that when you change 3, then you get these custom no problem is
Oh, yeah.
7.
Did I?
Wait, the second line is 4.
Yes. 7 minus
Yeah,
4 is
but
3.
Yeah, and then the P thing that you're supposed to do the
Oh yes, I did 7p3, didn't I?
yeah.
Thank you. I did 7p3, not 7p4. So we were right. We were right. So I made a mistake here. So we need to do 7. Thank you. NPR 4. There we go. Thank you, Marie. And we get 840. All right. So some calculators do have that NPR button, and if you can't figure out how to use that during work time, I can show you how. It's a little different on some calculators, but most are going to be like this. Thank you for fixing my mistake. All right. And we'll do more examples of using the calculator in just a bit. Okay. So it turned out to be 840 when we did everything correctly. So some examples where order matters. So let's say we have a race where 10 people are racing, and we want to know how many different ways people can come in first, second, or third. So Joe, Larry, and let's say Mo, Larry, and Curly, first, second, and third. Different than Curly, Mo, Larry, first, second, and third. Arranging them in a different way makes it a different thing. Yes.
Alright, so on your calculator, I'm so confused. Did you need that 3 in parentheses?
I did not.
Oh,
The mistake I made was I used a 3 in the calculation below instead of the 4.
oh yeah, I thought it was sort of stuff.
Right. And I double checked myself to make sure that way works. Because often when something happens in the calculator, putting parentheses fixes it. Another example, if you were forming a committee with a president, a vice president, and a secretary, so you could have 3 people on the committee, but a different person being president makes it a different committee. A different person being vice president makes it a different committee. So if you're putting them in the group of president, vice president, secretary, a different arrangement of those people makes it a different thing. Let's see. What's another good example? A baseball team So picking 7 people, picking a certain number of people from a baseball team versus having a specific batting lineup. So your batting lineup, someone's first, second, third, fourth. Changing that batting lineup changes what that thing is. So we're not talking about just a group of people. We're talking about putting them in a specific place in that order. So permutation, when we said order matters, it's when we're arranging that smaller group so that if we change the arrangement, it makes it into a different thing. All right, so let's do another example using permutations, and then we will talk about one other way of counting, and then we'll be done. So we have, this is the example I mentioned before, we have 10 people in a race. How many ways can they finish first, second, third? So the different arrangements of first, second, and third make it a different winning order. So we're changing the order, and it changes the thing. So the order matters here. So when order matters, we use a permutation. So we're going to calculate 10 P3. We're picking 3 things out of 10 where the order matters. So this is you plugging our numbers into our formula. What goes on top here? Blake? 10. 10. Factorial. 10 with the exclamation point. And on the bottom, we have something in parentheses. So what goes in those parentheses, Julianne? 10 minus 3 with a factorial. Perfect. So I can simplify this. 10 factorial. All right, can I do this? Cannot do this. Have to do inside the parentheses first. We're following the order of operations. Parentheses from PEMDAS. Parentheses come first. So this equals 10 factorial, 10 minus 3 in the parentheses is 7, 7 factorial. Now I'm going to make sure I do it in my calculator correctly this time. Go to my calculator. I'm not going to write out all those numbers. Calculator, let me clear all this, let me clear this. So I'm going to do 10. Go to the factorial. Divided by, and we're dividing by 7 factorial. My computer is need a second to catch up to me. Okay, enter. 720. Or I could do 10, make sure I do it right this time. Going to do 10 permutation, we're picking 3. Whoops, I messed up. I hit permutation. 10, probability, enter, 3. 720. Got to write that down. So I can do 10 factorial divided by 7 factorial, or 10 P3 in my calculator and calculate, and I get 720. So there are 720 ways that 3 people could come in first, second, and third out of 10 people. Questions on permutations? Okay. We have one last thing to talk about today. I know this is a long bit of notes. But what I want to do now is, for just a second, I'm going to pause, keep going here. So combinations. So we'll do like we did with the permutation. I'll tell you what they are, tell you how we calculate them, and then I'll give you some examples. The combinations of n things arranged R ways. Is that the way we said it with our permutations? Is that the way I said arranged? Oh, R at a time. That's what I want. I want to use the same phrase, R at a time. And for combinations, order doesn't matter. And the way we write that is NCR, C for combinations. And we also, you'll hear this in choose R. Some people will pronounce that in choose R. Kind of similar, n factorial over R factorial times n minus R factorial. And here we're saying that on all of these, R is smaller than n. So we're picking a smaller group out of a bigger group. So what's the only difference between combinations in our calculation and the combinations of permutations? So what is it? The order doesn't matter. The order doesn't matter. And in terms of our formula, what's different in a formula? There's this R factorial. So we're dividing by another number. So there are less combinations. So I'll show you how we calculate a combination, and then we'll do an example. So example, we'll do 7. We did 7p3. We'll do 7c3. 7 choose 3. So we'll plug into our formula, and if I remember correctly from last year, I think what Ms. Voss and I did was we either had these formulas written on the quiz or the test, or we wrote them on the board, so you don't have to memorize all of this. So this is 7 factorial. What is, so I kind of gave it away here. So what is R here? 3 factorial times 7 minus 3 factorial. We don't distribute the factorial. And I can simplify this. I'll just rewrite it again. Oops. All right. Another place to be careful. 4 factorial times 3 factorial is not the same as 12 factorial. So I can't multiply these together and then take a factorial. So I'm going to write over here, this is not 7 factorial over 12 factorial. I'm going to cross that out. Can't do it that way. Can't multiply these together. Have to do the factorial separately. So I'm going to plug this into my calculator now. This time I am going to use parentheses. 7 factorial divided by, I'm going to put a parentheses, 3 factorial times 4 factorial. And I get 35. So 7C3 is 35, 7P3 was 720. So a lot less combinations than permutations. The other way we can do it in our calculator is use the, I'm going to do 7 for the probability, and I have the NCR button here. I'm going to do 7, choose 3. And I get 35. So I can do it either way. All right. Questions on how to calculate combinations? All right, so there's some examples where we're picking things and the order doesn't matter. If we can pick 3 toppings out of 7 for a sandwich. So we're saying that a BLT sandwich is the same as an LBT sandwich. Doesn't matter what order we put the toppings on the sandwich, it's the same sandwich. I know a lot of us have some preferences about what order they go in. For me, the mustard has to go on the bun, and the tomato has to go on the meat, not the other way around. But it doesn't make it a different sandwich. Putting the toppings in a different order doesn't make a sandwich. Peanut butter and jelly is the same as jelly and peanut butter. It's that kind of idea. If we're playing cards, the order of the cards in our hand doesn't matter. A full house is a full house no matter how we arrange the cards. If we're just picking a group of 3 people out of the classroom, so I say I want 3 people out of the classroom, how many ways can I make a group of 3? That would be a combination, because the order of the group of 3 people does not matter. Doesn't make it a different group. Now notice that's different than when we said we wanted a president, a vice president, and a secretary. So that made it a permutation. We're just talking about a group, that makes it a combination. All right, let's look at one example with combinations, and then I want to pass out your homework, and we're going to do one of your homework problems all together. So we can choose 3 of 10 toppings. So kinds of sprinkles for our ice cream. How many ways can we pick our sprinkles? So if I pick M&Ms and crumbled up Heath bars and rainbow sprinkles, it's the same on top of my ice cream as rainbow sprinkles and then crumbled up Heath bars and M&Ms. So the order does not matter. Order doesn't matter, so we're going to use combination. So I'm going to calculate a combination. So how would I write this out? Second lunch is over.
Much better than.
You don't even like the phone? So how am I going to write, what is the thing that I'm going to do? Rand, how am I going to write this? What is the, I'm using a combination, how do I write my symbol? Start with a 10, C, 3, beautiful. 10C3 is what I want to calculate. So on the top of my fraction, I know this is going to be a fraction. What goes on the top of the fraction? 10 factorial. You say 10 exclamation point, I know what you're talking about. Okay, what's the first thing that goes on the bottom? Jason?
10 factorial.
10 factorial. The 10 factorial?
No.
3, right? R, it's NPR, so R goes here. 3 factorial. Then in the parentheses, Hunter?
10 minus 3.
10 minus 3, beautiful. 10 minus 3. Factorial goes outside the parentheses. I can't distribute, and I can't multiply. I have to do the factorials separately. So 10 factorial over 3 factorial. 10 minus 3 is 7 factorial. I'll plug this in my calculator. 10 factorial divided by, and I'm using a shortcut here. Whoops. Now it's better. Divided by 3. And I can just press this number 3 to get to the factorial. 3 factorial times 7 factorial. Close the parentheses. And I get 120. And I can also, in my calculator, use the NCR button. So I could do 10 probability, NCR 3, and I get 120. All right, questions on combinations? All right, what most students have a hard time with permutations and combinations is just calculating them's easy. Doing the calculations, your calculator does most of it for you. Figuring out when do we have a permutation, when do we have a combination, and when can I use the fundamental counting principle. My little kind of shortcuts, fundamental counting principle is when you're just picking how many ways you can arrange a certain set of things. We have 5 things. How many ways can I arrange these 5 things? Or when I'm putting things together. I have two shirts, 3 pairs of pants. I have 3 CDs and 2 CD players. How many combinations of CDs and CD players do I have? So we're putting those things together. That would be fundamental counting principle. Permutations and combinations are when we're taking a smaller group out of a bigger group. Taking smaller number out of a bigger group of things. Permutations, the order matters. So the different arrangement of things makes it a different thing. Combination order doesn't matter. Different arrangement of that smaller group doesn't change what that thing is. That's really the main thing. Yeah.
Is that the only difference? Or?
That's the only difference. Okay. So let me do this. I'm going to stop this.